I really want to start to, I don't think our guest needs introduction, but we should, and we're really honored to have Dr. Stephen Wolfram here with us. He's founder and CEO of Wolfram Research, creator of Mathematica, Wolfram Alpha, and Wolfram Language. He's actually, other than that, author of New Kind of Science and many other books. I just learned also about you have a book about second law of thermodynamics that I wasn't history. Yeah, that I didn't really appreciate. But I will, as I said, our guest doesn't need any further introduction, except that I do have to say, I see we have a lot of guests here outside of physics department. And we always in physics say one thing, that you should study physics, major in that, then you can do anything else. And our guest is actually a perfect example of this, that he has, studied physics in Oxford and Caltech, and he has actually, he holds a PhD degree in theoretical physics. He actually earned his PhD at age of 20, and his advisor, one of them, was no one else but Richard Feynman. And so, again, a perfect example of, do your PhD in theoretical physics or physics in general, and then you can do anything else. And thank you very much for coming here on such a short notice, and looking forward to your talk.
Thank you. All right, so, well, thanks for the introduction. My day job, as you probably know, is building things like Wolfram Alpha and Wolfram Language and so on. For a long time, we built them mostly for humans. In today's world, we're also building them for AIs. There are probably about as many AI users of our technology as there are human users at this point. But I'm not going to talk about that. The reason I built those systems, the number one reason was because I wanted to have them to use myself. And so my kind of hobby in life is doing basic science, and I get to use these tools I've been building for many years to do basic science. About 5 years ago, made kind of a breakthrough in fundamental physics, whose consequences are certainly not fully known yet and won't be known for a long time. But I thought I would tell you a bit about that, about what I figured out, and about what some of the emerging consequences are. And things happen, I can tell you some things I figured out last week and so on about Feynman diagrams, as it turns out. I guess I should sort of set the things that I've been interested in as sort of foundational questions about physics, which turn out to be related to foundational questions about math, surprisingly have turned out to be related to foundational questions about biology and machine learning, and some other things. They all turn out to be quite related, and I can try and explain that. But maybe to give a bit of the personal backstory, I started doing physics when I was a kid, and was really interested in particle physics. This was in the mid to late 1970s, when particle physics had just sort of discovered quantum field theory, and lots of things about QCD and other kinds of things could be figured out. And so I had the fun time as a teenager of working out lots of stuff in this rapidly moving field, and stuff that sort of survived to today. But the main thing that the meta thing that I discovered was that, when you do things like theoretical physics, you end up having to do all these elaborate calculations. The main meta thing that I discovered is you could use computers to do those things. And so I started my original motivation for building what eventually became Mathematica, Wolfram Alpha, and so on, was that I was trying to do calculations about things like Feynman diagrams and quantum field theory, and I didn't want to have to do all those complicated mechanical calculations myself. But then around 1980 or so, I got interested in sort of a foundational question in science, which is sort of how do complicated things get to be made in the natural world? Whether they're things like turbulent fluids with apparently random flow, or whether they're things like snowflakes, or whether they're things in biology. How do sort of complicated things end up getting produced? And I sort of assumed, with all this fancy mathematical physics that I knew from quantum field theory and so on, that this would be an easy problem to solve. Turns out that wasn't the case. So then, around the beginning of the 1980s, I kind of said, well, what's going wrong, so to speak? And I kind of started thinking about what is the sort of, when we make models of things, what raw material are we using to make those models? And so I sort of was thinking if we're making a model of things, there should be some definite rule that the system is following. The question then is sort of, well, what kind of a rule is that? And one is used to using, mathematical equations and so on. That's been the kind of 300-year tradition of these things. But I sort of started thinking, well, what if you just use sort of arbitrary rules of the kind that, for example, you can capture in a program? And so the question then arose, well, there's sort of a basic science question. If you just pick a program at random, what does it typically do? Well, so I started investigating that question, and I could sort of run the experiment again. It's the type of program that I liked a lot at that time, still like, is a thing that's called a cellular automaton. And kind of the idea, the simplest case is just a line of cells. Each one is either black or white. And then in a series of steps, you update the color of each cell according to a rule that depends on the color of the cell, of that cell on the previous step and its two neighbors. So with that particular rule, you can say, well, what does the thing actually do? And we can just work that out here. It got easier over the years to do this. So with that particular rule, very simple rule, behavior is also very simple. So the question is, well, is that generally what happens? Let's change the rule a bit, change it something like this, change it here. Instead of producing, we have a simple rule. Again, it produces a very simple pattern. Maybe change the rule one more time, something like this. Try it again. Well, it makes a slightly more complicated pattern. If we continued that pattern a while longer, we'd find that it will be very intricate, but it still has a very kind of regular form. It's a nested pattern. So the question then is, what happens out in the sort of computational universe of possible programs? It's sort of a very basic science question. What do these programs typically do? It's something that, if you do computer science doesn't usually mean this kind of natural science-like science, but you can do kind of natural science-like science about computational things. So, for example, here, let's go ahead and just, we can enumerate, there are 256 possible rules of that particular kind. We can just look at what all of them do. So we can just say, let's make a table of these with n going from 0 to 255. So this is our sort of minimal computer experiment. And many of these rules do just very simple things. Some of them make these nested patterns. But then we get to rule number 30, which is my all-time favorite science discovery, because look at what it does. You started off from just one black cell, and let's look at the rule it's following. So we can just let rule 30 here, and then let's see what it does if we run it. Well, it doesn't do something simple. On the left-hand side, you can see there's a certain amount of regularity, but if you look at something like the center column of this pattern, you find that for all practical purposes, it's completely random. It's actually, we used it for many years as a pseudo-random generator in Mathematica. It's passed a great many tests of randomness. So this is a very surprising thing. You can start with a rule that simple and end up with behavior that complicated. And it's kind of something which took me quite a few years to kind of get intuitionally used to this point that out in the computational universe, complexity is sort of there at every turn. And I think it's sort of in some sense, it's the secret that nature uses to make the kinds of complicated things it does, is that out in the universe of all possible rules, many of them do these very complicated kinds of things. Well, so you can ask, well, what are some sort of broader scientific questions you can ask about this? One question you might ask is, can we predict what will happen? If we ran this for 1 billion steps, can we predict what the outcome will be? And in a sense, the big point of a lot of kind of at least the mathematical sciences has been, let's make, we're doing successful science if we can make predictions about what's going to happen. And we have a way to kind of jump ahead. If we have some model for some idealized two-body problem of Earth going around idealized sun, then we could just have to trace 1 million orbits to find out where the Earth will be 1 million years from now. But actually, we know we can just write down a formula and plug in the number 1 million and immediately get the answer. So we have sort of the tradition has been that science allows us to kind of make predictions and jump ahead. So the question is, what happens in a case like this? We can clearly figure out that if we just explicitly, if we want to know what happens after 1 billion steps, we can run this for 1 billion steps and see what it does. But the question is there any shortcut? Is there any way to sort of computationally reduce the behavior of this system? So the interesting thing is that it seems that there isn't. It seems this is an example of what one can call a computationally irreducible process, where sort of the only way to work out what will happen is essentially to run each step and see what happens. So you can ask, well, why would something like that be true? Why would there be, where does this phenomenon of computational irreducibility come from? It's all mixed up with things like Gödel's theorem and universal computation and so on, but you can explain it in the following kind of way. So the question would be, if you look at a system like this or one of these other cellular automaton rules, you can say, try and characterize what it's doing. You can say, well, it's doing a computation. It starts off from some initial condition, it computes its successive states, comes out with some result. And you can ask, well, what kind of a computation is that? Sometimes it's a really simple computation, like it's an identity computation. It just sits there with a single black cell and does nothing. Sometimes it's a more complicated computation. But the question is, you can ask sort of, what are the levels of computation that can be achieved by these different types of systems? So a kind of principle that I think is a very general principle is a thing I call the principle of computational equivalence. And it basically says, as soon as the system doesn't show obviously simple behavior, the computation that its behavior corresponds to will be as sophisticated as any other computation. So in other words, when you get above some very low threshold, you've kind of maxed out the computational sophistication of your system. So one knows about things like universal computation, the sort of the big idea that made software possible and so on, that comes from the originally 1920, but most famously 1936. This idea that, if you want to do different kinds of computations, you might have thought every different kind of computation you want to do, you'd have to buy a different computer to be able to do it. But what was realized was that you could make a universal computer that has the feature that by just feeding in different initial conditions, you can make that universal computer emulate any other kind of computer and do essentially any kind of computation. But what one had always assumed was that things, to get to that sort of level of computational sophistication, you had to sort of put a lot of effort in and build a fancy CPU and things like this. What the principle of computational equivalence says is that actually things like universal computation, this maximum level of computational sophistication, is extremely common and ubiquitous, including not only in these abstract systems, but also, for example, in systems in nature. So what implications does that have? Well, it means if you're trying to make a prediction about what this system will do, the system is doing a certain computation. You, as the predictor of the system, are also doing a computation. The principle of computational equivalence says those computations will be of equivalent sophistication. So you, as the human with a brain, or the computer, or doing statistics, or whatever else you're doing, those kinds of computations are no more sophisticated, according to this principle, than the computations that are going on in this very simple system, in this system here with a very simple rule. So that's the origin of the idea of computational irreducibility, is that this system is doing a computation that's as sophisticated as the computation that you can do in trying to predict what the system will be able to do. So anyway, this idea of computational irreducibility has all kinds of consequences. It basically is showing one from sort of within science fundamental limitations on what you can expect to kind of get out of science. And there are many, many consequences of this. I mean, if you go to sort of modern times and you're thinking about things like, AI ethics or something, and you're asking the question, can we make sure that the AIs only do the right things and not the wrong things? Well, computational irreducibility says there's sort of a problem with that, because computational irreducibility kind of tells you can't, in general, predict what's going to happen except by running it and seeing what happens. So if you insist that you have a system where you can jump ahead of it, you can go ahead of it and know what it's going to do, you have to have a computationally reducible system, which means you're sort of not using all the computational capabilities that you might. So you kind of have this choice. You either have to reduce the computational capabilities of your AI, or you have to live with the fact that occasionally it will do things that you don't expect. I mean, there are many, many consequences of computational irreducibility. We can talk about more of them. It's kind of an interesting thing that kind of tells you, among other things, you'll never run out of science to do. There'll never be a point where you've discovered all science that you could discover, partly because within any computationally irreducible system, there are inevitably an infinite number of pockets of computational reducibility. So for example, in this particular system, there's a certain amount of regularity over on the left. It's inevitable that there will be a whole sort of hierarchy of regularities that you can discover. You'll never run out of those things to discover. Okay, so this was stuff that I figured out in the early 1980s about kind of this sort of foundational way of thinking about computational systems. I might mention, I'll give a shout out to the second law here, since that was mentioned. Let's see. So in fact, this was actually, in my personal history, this was actually got me started in this direction in the first place. So second law of thermodynamics is this idea that sort of things tend to get more random. If you start with a bunch of molecules sitting in one corner of a box, then chances are, after a while, those molecules will be sort of randomly distributed in the box. So the question is, what is the origin of this phenomenon? And it's been a very confusing thing. It was originally talked about first in the mid-1800s, and people sort of thought they kind of figured it out by 1900, but they really didn't. And textbooks are usually pretty, they say things like, they argue that the second law shows that sort of things will degrade to randomness as you go forwards in time, and they say, well, actually, you could flip around that argument and say the same thing would work backwards in time, and they'll end with things like, this point is often puzzling to the student. But it's the question is, why does this phenomenon happen? Why does it tend to be the case that things sort of get more apparently random? Well, you can kind of look at, you can kind of study this, and you can, there's a nice 3D picture of those things bouncing around. You can kind of simplify the situation. Those are square things. You can simplify it more and put it on some kind of grid. You can, eventually, you can get it down to the point where you're looking at just a one-dimensional thing, and you just have, in fact, you can even do it with a simple cellular automaton, if I can only find the relevant picture. Let's see, sorry. This is, oh, here we go, there's a good picture. So this picture kind of already shows part of the answer. This is, if you start this particular cellular automaton, it's a reversible cellular automaton because one's interested in what one of the sort of features of things is that, well, that you have a system that appears to be reversible, yet the kind of the large scale behavior of systems tends to seem irreversible. You break things and they end up in little pieces. They don't tend to spontaneously assemble themselves from the little pieces to the big thing again. And that's kind of a different manifestation of the second law. But you start this off from a configuration where you basically have just a set of cells in the middle of the region. You evolve it forwards in time, and it becomes progressively sort of more random looking. Turns out also, because it's a reversible system, if you evolve it backwards in time, it will similarly get more random looking. Well, the phenomenon of the second law is that, yes, it gets more random looking. It is not, in some sense, the sort of true information content of what's here is no different than the true information content of what's here. You could always go backwards from here and get to this if you can just follow it precisely through all of these steps. But it turns out one can think of the second law as another manifestation of computational irreducibility. The basic thing that's happening, some version of it you can think of, is you start off with these initial conditions that are pretty easy to specify. You end up, as the dynamics of the system goes forward, you end up essentially encrypting those initial conditions to the point where a sort of computationally bounded observer is not able to deduce that the initial conditions were simple anymore. So what's happening is this dynamics of the actual evolution of the system is an example of computational irreducibility. And if you are just stuck with observing the system at a point like this, you have to do sort of an irreducible amount of computation to deduce that the system came from that simple initial condition. And so the reason it looks random to you is because we are sort of computationally bounded in what we can do, the experiments we can do, the things we do with our minds and so on, particularly relative to things like gas molecules, which there are very large numbers of in very small volumes, it's our computational boundedness interacting with the computational irreducibility of the underlying dynamics of these systems that leads us to believe in the second law, to believe that the best we can say about what's happening at this stage is that it looks kind of random. So in terms of entropy, entropy is kind of telling you the log of the number of states of a system that are consistent with something you know about that system. And in this case, what one's saying is that things are sort of random, seem random enough to us that we just sort of have to throw up our hands and say, we know nothing about the system other than maybe how many particles are in it or how big it is or something like that. And therefore, it has to have maximal entropy because all those different possible states of the system, we can't distinguish between, we're saying we don't know which of those states it's in. So, in any case, there's this connection between computational irreducibility and the second law. And since the second law was mentioned, it's one of my favorite topics, I thought I would mention this. It's also relevant that this interplay between our computational boundedness as observers and the computational irreducibility of underlying dynamics will show up again when we talk about things about fundamental physics. Okay, so turning to fundamental physics, there's sort of a question that people have asked since antiquity, I guess, which is, what's at the lowest level, what's the universe made of? Is it continuous or is it discrete? Is it made of atomic kinds of things or does it kind of flow like a fluid? And that was, people asked that forever. In the 1800s, people were sort of wondering, are there molecules that make up matter or not? By about 1900, that was resolved. Yes, there are molecules that make up matter. Matter is discrete. Then soon afterwards, photons are there. Light can be thought of as discrete. At the time, beginning of the 20th century, most physicists believed that space was discrete as well. And all of the standard big names of physics at that time, I didn't know this until recently, and they published almost nothing about this, and so it's kind of hard to track down the history. But they all believed that space was discrete, but they couldn't make it consistent with relativity. Anybody who had sort of a model of space that was sort of discrete cells and things like this couldn't make that work. We were talking earlier about Heisenberg, and I have to tell a story about Heisenberg. Heisenberg, I learned this only recently, was trying to make a discrete model of space, just couldn't make it work. Eventually he said, forget all of that, I'm just going to think about the initial states of systems and the final states of systems and not worry about what happens in between. And that was the invention of the S-matrix. So anyway, so the question is can one think about space as being discrete? Can one think about, what might the universe sort of be made of? And I'd sort of in the 1990s, I had kind of first started thinking about this, and then about 5 years ago, a little bit more than 5 years ago, made sort of a breakthrough in this whole direction. And let me show you what I figured out. So sort of the big idea is, what's the universe made of? Well, we imagine that it's just made of discrete things we might call atoms of space. And the only thing we kind of know about those atoms of space is how they're related to other atoms of space. But there's no geometry, there's no intrinsic space there. There's nothing where we say there is a space and we're putting things in it. It's just there are a bunch of discrete things we can call atoms of space. And each atom of space is related to other atoms of space. So we might have some little graph that represents the relationships, the sort of Venn diagram of the atoms of space. Well, then we say, how does time work? First of all, we imagine that sort of the only thing that's in the universe is space. And every feature of what we see in the universe, electrons and quarks and photons, all those kinds of things, those are all features of this giant network that represents the structure of space. So the only thing in the universe is space, and it is this network. So what's time? Well, time is kind of the idea of kind of a progressive computation from one state of this network that represents space and everything in it, and another state of the network that represents space. So it's another thing that I think was sort of a wrong turn in 20th century physics was the idea that space and time are the same kind of thing. In these models, it's really not the case. Space is kind of this extent of this graph, or actually hypergraph, and time is the progressive doing of computation to compute the next state of the universe. So you can set things up. It's kind of like, this is a typical example of kind of the evolution of some graph that's being rewritten, progressively rewritten by simple rules. It's kind of a little bit like a cellular automaton, except that here, these rules just say, if you see a little piece of graph that looks like this, rewrite it into one that looks like that. And you keep doing that for a really long time, and you start getting, and you get some very big, complicated graph. And the question is, well, what does this limit of this graph, what does it actually do in the limit? Well, okay, to give another sort of preamble to this, if you look at molecular dynamics, look at a bunch of molecules bouncing around, and you know that they obey the laws of mechanics locally, you can ask, what is the large-scale behavior of those molecules? We talked about the second law, but if you are looking at something which is not, for example, uniform in space and so on, what you end up with is fluid dynamics. That's sort of what is at a microscopic scale molecular dynamics, at a macroscopic scale is fluid mechanics, and the Navier-Stokes equations and all those kinds of things. The derivation of the Navier-Stokes equations from molecular dynamics, everybody sort of assumes it works. It's never been mathematically rigorously done. People worked on it a lot 100 years ago, didn't really get that far, hasn't really been gotten that far since. But at a physicist level, it's just fine. At a mathematician's level, it's definitely not fine. But that derivation, by the way, now that we understand things about computational irreducibility and the origin of the second law, one at least has a leg up in doing that derivation, although it's pretty clear that it's a complicated story of kind of computation theory and so on, not just a story of for example, continuous mathematics. But in any case, the big point there is that you have these discrete molecules underneath, and the limit of that on a large scale is the Navier-Stokes equations. And that's true pretty much regardless of the details of those molecules, whether they're water molecules or air molecules, you still get the Navier-Stokes equations. The parameters may be different, but the form of equations is the same. So molecular dynamics, the large-scale limit is Navier-Stokes equations. You can ask the question, if you're looking at graph rewriting, what is the large-scale limit of graph rewriting? Well, the sort of big result with many footnotes is that the large-scale limit of graph rewriting is the Einstein equations. So let me try and explain that. So that's the Einstein equations being the equations that determine the structure of space-time. And so the first thing you have to say is, well, what can we say about one of these graphs? We don't even know what dimension the thing has, what dimension of space it might correspond to. If you take a look, this is one particular example. If you run this for a while, its limit looks like this. It really looks very much like it's knitting sort of a two-dimensional structure. You can try other things. Here's another one, I think, that makes a kind of curved two-dimensional surface. So the first question is, when you take the limit of this very big graph, what is the dimension, what is the effective dimension of that large graph? So how do you work that out? Well, I mean, the graph itself, you can take one graph, you can lay it out on a page in all kinds of different ways. But if you can ask something like this, you can say, let's imagine we start at a particular node in the graph, and we progressively go distance 1 on the graph away from that node, distance 2, and so on. We build up essentially this ball in the graph, and we ask how many nodes, after we go r steps in this procedure, how many nodes do we enclose in that ball that we get after r steps? And so then you say, well, if that increases roughly like r to the d, then we can say this is approximating d-dimensional space. So that's sort of the beginning of things. And you can work out, you can actually plot that. You can do that construction for a lot of these things, and you can see that, yes, this particular one is about a 2.6 dimensional space. Now, if you ask, how does that work, this sort of limit of the growth rate of the volume of this geodesic ball, how does that work? If you look at the formula for that, the leading term is r to the d. The first correction to that is 1 minus the scalar curvature of the space. So, for example, usually the area of a circle is pi r squared, but on a sphere there's a correction term to that depends on the radius of the whole sphere. And sort of the generalization of that is something that works in any number of dimensions that says that the correction term is actually the Ricci scalar curvature. And so you can then say, well, as we're looking at this limit of these graphs, we can then ask questions like, if we have a certain dimension, we have some correction that's proportional to the Ricci scalar curvature. That's a very encouraging start, because the Ricci scalar is a piece of what appears in the Einstein equations. The sort of bigger, well, in the end, okay, I have to explain the Einstein equations, I have to explain a whole bunch of other stuff. But I mean, fundamentally, the Einstein equations give you a relationship between the curvature of space-time and the density of energy momentum in space-time. So one of the questions here is, well, what is energy momentum in these systems? And I had thought we'd never be able to figure out what energy momentum is until we understood what particles are. Turns out I was overly pessimistic, because to say what might particles be in these systems, presumably particles are something like some sort of topologically stable structure in this network that is somehow persistent with respect to sort of the rewritings of the network. A bit like in a fluid, for example, you might have a vortex which is kind of topologically stable as it moves through the fluid. So similarly, you can look at the same kinds of things for these graph rewriting processes. Unfortunately, the mathematics of this is not well developed. I mean, a few years ago, I was talking to some fine leading graph theorists I was trying to describe the problem, and they said, come back in 100 years, and we may know a little bit more about that question. So this is one of these, you're kind of on your own figuring things out. But in any case, so what does energy correspond to? What energy corresponds to, it seems, is well, okay, it's essentially the density of activity in the network. Let's see if I can find a good picture of this. This is okay. So in this network, you have these. Where do I have a picture? I'm sure I have a picture of this. Sorry. There we go. Well, you're continually rewriting this graph, and there are these, what one can think of as rewriting events. A rewriting event is something where a little piece of graph gets rewritten by another piece of graph. And you can draw a causal graph that represents the causal relationships between those rewriting events. So, for example, one rewriting event might consume certain atoms of space and produce other atoms of space. And then another rewriting event might take the atoms of space that were produced and consume those again. And you know that that second event has to be sort of later in time than that first event. It has to be time-like separated from the first event. It provides kind of a succession of a definition of sort of the what comes after what. In mathematical terms, it's going to make a partially ordered set of events that are the update events. Okay, so that graph that you can make a causal graph that represents the causal relationships between those events. And so this is just saying that each of the yellow dots is an event, and it's connected to events which are going to make use of its output, so to speak. So if you think about the event as a function or something, it's the result from that function is going to be an argument to the next function, so to speak. So, okay, what can we say about these causal graphs? Actually, for example, these causal graphs are ultimately the thing that an observer is going to be able to pay attention to. The observer is embedded within this. There are events taking place in the observer, there are events taking place in the outside universe. It's only sort of the relationship of those events that one's actually able to make observations of. And so there are all kinds of things one can do with these causal graphs. For example, the sort of successive nodes down here are time-like separated. If we are trying to think about, well, what corresponds to simultaneity of these events you can think of as being events happening in space-time. What constitutes a space-like hypersurface, a kind of a surface of simultaneous events? Well, there are many different simultaneity surfaces that you can draw consistently through this causal graph. And the fact that you can draw many such consistent simultaneity surfaces is what leads to special relativity in these models. The fact that it in the end, well, again, I have to explain a few more things, but there's a phenomenon we call causal invariance, which essentially has to do with the fact that regardless of how you slice this, regardless of what sort of sequence of slices you make, so long as all those slices are consistent, they don't involve, they involve events which can be thought of as separated in space and not separated in time. As long as you do that, you end up always getting sort of the same answer for things that you measure. So in any case, these causal graphs are kind of the main raw material of what's happening inside these models. And one of the things that one can deduce from this is what energy is. And what energy turns out to be the flux of causal edges through space-like hypersurfaces. So roughly, it's the density of activity, the density of updating activity in the network, but slightly more precisely, it's if we draw a space-like hypersurface across this, it's the number of causal edges that poke through that space-like hypersurface. And momentum is the corresponding thing of the number of causal edges that poke through time-like hypersurfaces. And mass is related to the essentially the extent to which you are essentially you can think of every one of these causal edges as being the edge of a light cone, and mass has to do with the extent to which you have a series of events that remain kind of inside that light cone. In any case, that was a long explanation of there is a definition of energy that doesn't require yet knowing how particles work. And then the big result is that that density of energy affects the curvature of space-time in the way that the Einstein equations say. And one thing that's really cool is that in these models, you can actually make pretty mechanical kinds of arguments for how lots of physical phenomena happen. So for example, standard physical phenomenon, time dilation and special relativity. So in these models, you can say, imagine you have a thing, maybe it's even a particle, and it's at a particular place in this, network. That thing will update itself by doing these rewrites in the network, and it will use, there'll be a certain number of events. It will use a certain sort of computation budget to update itself. If it's just in one place in the network, it gets to use that whole computation budget, sort of updating its own state, sort of progressing through time. On the other hand, if it's moving, it's got to use some of its updating budget, some of its computation budget to recreate itself at a different place in space. And so it doesn't have as much computation budget to use to update itself in time. And so that's why, I mean, that's a very qualitative argument, but you can fill in a bunch of math around that. But that turns out to be why you get time dilation, that you're using up some of the computation budget on motion, and so you don't have as much to actually do the evolution of the system through time, so time effectively runs slower for that system. And you can also figure out things like gravity. In these models, in this hypergraph, you can define geodesics, shortest paths. You can define the shortest path in the graph easily. And you can say, well, what, if we think about these shortest paths in the graph, how are shortest paths in the graph affected by the presence of updating in the graph? And it turns out that the presence of updating deflects shortest paths in the graph, which is essentially what gravity is doing. The presence of energy momentum or mass is deflecting geodesics. So it's causing, which is so kind of the story of gravity, is that the presence of mass deflects shortest paths, which you can represent in terms of curvature of space and so on. Okay, so anyway, there are lots of things. I mean, there's lots of interesting stuff that happens in these models, even the level of thinking about space-time. So, for example, if you think about the early universe, the expectation in these models is the early universe probably started more or less infinite dimensional, and gradually, as the universe progressed, it evolves to something that sort of cools down to be roughly three-dimensional. We don't know how to derive the number 3. We don't know we don't know why it ends up as three-dimensional. My guess, as I'll maybe talk about later, is that it is three-dimensional primarily to observers like us, and that is not really an intrinsic feature of the universe. But that's sort of a separate thing. But the picture is sort of starts infinite dimensional, gradually sort of cools down to be three-dimensional. You can also think about, well, so one of the things that's interesting in the kind of space-time domain is what experimental implications can you imagine from these models? Many of the experimental implications depend on what the elementary length is. If you ask things like, changes in the propagation of gravitational waves, things like this, most of those things seem to depend on the size of the elementary length. We don't know what the elementary length is. I have a pretty lousy argument. Well, one thing we do know is that the elementary length is much smaller than the Planck length. And I have a kind of lousy argument that it might be of order 10 to the minus 100 meters, which is very small and hard to, in the beginning of the 20th century when people discovered molecules, they were lucky that the experimental techniques that existed at the time, like looking at Brownian motion with microscopes and so on, you could actually see the pollen grains getting kicked around by molecules. The molecules weren't too small for that to be possible. So we may or may not be lucky with detecting something which, making a sort of gravitational microscope that can see to the elementary length. But there are other effects that are very weird that these models predict. So one of the effects is the presence of dimension fluctuations. Because dimension is now a dynamical variable, it's not sort of built in as 3 dimensions. It's something which can vary with time and vary with position. And in fact, there's probably a duality between thinking about general relativity in terms of curvature of space and thinking about general relativity in terms of dimension change. But in any case, you can think about sort of perturbations in dimension, possibly ones left over from the early universe and so on. And then there's all kinds of interesting physics problems which have not been adequately investigated about what sort of weird gravitational lensing happens when you go through a region of 3.01 dimensional space or some such other thing. So in any case, there's all kinds of interesting stuff there. I'll mention another thing about space-time, which is one of the mysteries that's been around 100 years or so is dark matter. And there's sort of a question of what is dark matter. I have this kind of slightly funny guess, which is it actually resonates with a piece of the history of physics. In the 1800s, people wondered what heat was. And they knew that heat could flow from one substance to another. And so what can flow? Well, the things that flow are fluids. And so then what was invented was the idea of caloric fluid. And caloric fluid, of course, isn't really what heat is. Heat is microscopic motion of molecules and so on. So my guess is that dark matter is similarly very misnamed. The dark matter is not matter at all, but instead is a macroscopic manifestation of the microscopic structure of space-time. And so the short version of that would be to say that dark matter will turn out to be space-time heat. We shall see. I can show you. Let me just show you one thing if I can find it here, and then I want to talk about some. Let's see. Here we go. So this is. If I can show this, yeah. Here we go. This is a little video of kind of the first moments of some version of a universe in rewriting of a graph. And the fact that it's wobbling around like that is absolutely irrelevant to the physics of what's happening. This is just the rendering of the thing for us to be able to see it projected into 2 dimensions. Well, if you go sort of much later in the history of this universe, you can kind of get some vague. This is sort of an attempt to simulate 2 little black holes. It's easy to understand what black holes are in these models. They're basically places where the causal graph, where there's an event horizon, it shows up as a disconnection in this causal graph. This is a thing where you kind of have to start it off by sprinkling. We can't realistically get to having black holes. We have to start off with sort of traditional general relativity, and then kind of use these microscopic dynamics on this network that you get from an initial kind of continuous metric. Anyway, you can see these little black holes wobbling around, and eventually you see they should merge together. And the claim is that you can measure little gravitational waves and so on, and they actually do seem to agree with what's observed, which is encouraging. It helps very much that black holes are kind of scale invariant. you can have a very tiny one that's only 10,000 nodes across, and it will behave pretty much the same as a kind of a big black hole that's macroscopic size. So and by the way, one thing to realize is that all that sort of wobbling around that you see is kind of the fact that space is knitted together by this series of updating events that are happening. If there weren't updating events, space would not be, there would be no coherent kind of thing like space. So the existence of space is a consequence of the fact that it's being continually rewritten like that. All right, so another big thing that one thinks about in physics is quantum mechanics. And one of the things that is sort of interesting about these models is that quantum mechanics ends up being not something that you sort of say, oh, we have to put that in some kind of arbitrary, bolt-on kind of way. Quantum mechanics is inevitable in these models. And the reason is this, that when you think about rewriting this hypergraph and you ask, well, that you're just saying, if there's a little piece of graph that looks like this, it will be rewritten into one that looks like that. But the point is there are many places where that rewriting can happen. And what happens is that that means that you essentially have many paths of history. So to say the sort of the basic thing about quantum mechanics, the big difference between classical physics and quantum physics ends up being, in classical physics, you throw a ball, there's a definite trajectory that it follows, and that's how things work. In quantum mechanics, kind of the concept is there are many different paths that the system follows, and all we get to talk about are the probabilities of those different paths. Well, in these models, what happens is there are many different possible rewriting sequences that could occur, and we can kind of make, we call them multi-way graphs, that just show the different paths of history, basically, corresponding to those different sequences of rewritings. And so this is a much simpler system, not a graph. This is just a string of A's and B's, and we have a simple rule that says how to rewrite those strings, but there are different possibilities, like the BBB string here can be rewritten either to AB or to BA, and we can think about these different edges as being different paths of history. And so we can then kind of take, in our whole big network, we can make this, we can sort of identify all these different paths of history, and we can kind of, let's see, where do I have a picture of that? We can say we've got all these different paths of history, and we can say let me look at what the relationship is between let me ask what the relationship is between different elements at a particular. Okay, so this is we slice this up into a series of time slices, and then we ask for each path of history. We can think of these as we want to. We can think about them as quantum states. We ask the question: what is the sort of relationship? What is the map of entanglements between these quantum states? We can kind of ask, what is the common ancestry of these different states? And from that common ancestry, you can build up a graph that represents that kind of common ancestry. It represents the relationship between those states, the kind of map of entanglements between those states. And then we can look at the limit of this when we have a large system, and we can think about sort of the space that is the limit of this entanglement map. We call it branchial space, the space of quantum branches. And so branchial space has all kinds of interesting properties, but we can start asking questions like, how does motion work in branchial space? And, well, this is, I mentioned before that the Einstein equations show up as being this relationship between activity in the network and the deflection of geodesics in the network. Well, what happens in an analogous thing happens in these multi-way graphs and in branchial space. Oh, I should explain another thing. This is, again, not well tied down, but the indication is that position in branchial space is related to quantum phase. Exactly how that works, there's a lot that we know about that and a lot that we don't know about that. But roughly, position in branchial space is like quantum phase. And one of the things that also happens in these models is that in quantum mechanics, one thinks of quantum amplitudes, which have both a magnitude and a phase. Just as we're kind of unbundling space and time, we also think that one should unbundle magnitude and phase of quantum amplitudes. The phase is kind of position in branchial space the magnitude is basically the counting of the number of paths in this multi-way graph. But in any case, there's a thing you can do where you're asking, how does the presence of rewriting, essentially the presence of energy momentum, affect kind of geodesics in this multi-way graph? Anyway, the end result is that what happens is the presence of energy momentum deflects one in branch yield space. So in other words, the presence of energy momentum is changing the phase of the thing that one has. And so the end result seems to be that the path integral, which is telling one how energy momentum, the Lagrangian density, affects quantum phase, that what one's seeing is the really nice thing is that what in physical space is energy momentum deflecting geodesics in physical space, the same thing happens in branch yield space, except that while that corresponds to the Einstein equations in physical space, it corresponds to the path integral in branch yield space. So we have the very nice claim that essentially the Einstein equations and the path integral are coming from the same thing, but just played out in different kinds of space. So in any case, lots of fun things to say about how quantum field theory works and various related things. I mean, I suppose one obvious. Well, let me try and move on to some other things. But I can talk more about this if people are interested. So we have this model which does surprisingly well at reproducing general relativity. We can certainly reproduce quantum mechanics. We can sort of see that we can compile quantum mechanics into these multi-way graphs, and we can solve problems about quantum circuits in terms of multi-way graphs and so on, just as we can do numerical relativity effectively using graph rewriting. So then the question is, okay, so let's go a little bit deeper in sort of the rabbit hole of understanding foundationally how this works. So one question would be, if you're successful and you say, okay, at the end of this, you say, I've got this rule, and this rule reproduces our universe. That's sort of a weird situation to be in, because the thing you would then be asking is, well, why did we get this rule and not another rule? Why is our universe the one that has rule 3712 or something, as opposed to any other rule? And for a while, I was really confused about this point. And then I realized that just as what happens in these networks is that there are many possible rewritings that could occur, and quantum mechanics is following all those paths of rewriting, so you can also think about there being many possible different rules that can be used for that rewriting, and what if the system just follows all of those possible rules? So you have a system you have something which is essentially following all possible computational rules. You're saying you start the system off, and then it's as if you're doing Turing machines or something, you start off all possible Turing machines in all possible initial states, and you let them run for an infinite time. What do you get? It sounds like a total mess. It sounds like, how could you ever conclude anything from that? But the big point is that you can, let's see, if you start off with, well, okay, there's a little Turing machine, there's the rule for a Turing machine, there's what a Turing machine does, it just has this head that goes back and forth, rewriting things. And you can then say, well, what about a multi-way Turing machine where it has multiple things that it can do, and then you can build up this multi-way graph that represents the different possible states, the different transitions that the Turing machine can go through. Well, if you do that, if you say, well, let's let the Turing machine follow all possible rules, you start building up this big graph that represents sort of the structure of this thing from all possible Turing machine rules. The limit of this is this thing we call the ruliad. It's kind of the entangled limit of all possible computational processes. And that's it's sort of a thing that has a lot of structure. And the main reason it has structure is that two different rules may end up leading to the same state. So you have something which, if it was every rule is sort of leading to something different, you just have a giant tree. But because there are equivalences, the thing ends up having a complicated structure. So okay, so you have this ruliad object, and the question is then, what can you say about this ruliad object? Well, one thing you start to be able to say, if this ruliad object is the entangled limit of all possible computational processes, then among other things, the computational process that is us must be somewhere inside this ruliad. And so then what you end up wanting to ask is, what does an observer embedded within the ruliad observe about what is in the ruliad? And you might say, well, how can you say anything about that? Well, the important thing is you have one extra piece of information. I mean, the ruliad is sort of an inevitable object that once you have the definition of the idea of computation, it is inevitable that there is just this one single object that is this entangled limit of all possible computations. But an observer, the question is, what's that observer like? Well, we know several things about us as observers. One that I already mentioned in connection with the second law of thermodynamics is that we are computationally bounded observers. We have finite minds. We're only able to sort of take in mind a limited amount of computational, a limited amount of computation. That's one thing we know. The other thing we know is that we believe that we are persistent in time. We believe that there is a thread of experience that we have that sort of goes through time. I mean, if we think about things in terms of these models, at every moment in time, we are made of different atoms of space. So it's kind of weird that we think that we are persistent, but we have this belief that we are persistent in time. And so those are two important facts about us as observers, that we are computationally bounded and that we believe we are persistent in time. Well, it turns out that seems to be the case that those two facts alone, combined with this idea of the ruliad, kind of give one inevitably laws of physics. So in the case of the second law of thermodynamics, talked about before, once you have the idea of computational irreducibility and you have this fact that observers like us are computationally bounded, you inevitably get the second law of thermodynamics. The same thing seems to be true for general relativity and for quantum mechanics, which to me is super surprising because I never would have expected that one will be able to derive general relativity from any kind of sort of foundational principle. I assumed that general relativity was just a thing that happens to be true about our universe. Same with quantum mechanics. With the second law, people had suspected for a long time that the second law might be somehow derivable from something more principled and low level. But what seems to be the case, and sort of a big result of the sort of direction I've been going, is that the laws of physics, the three main laws of physics that emerged in the 20th century, namely statistical mechanics, the second law, general relativity, and quantum mechanics, all seem to be derivable from this computational idea of the ruliad, plus the contingent fact that we are observers of the kind we are, which doesn't need to be the case. I mean, we could be very different kinds of observers than the ones we are, but we happen to be computationally bounded observers who believe we're persistent in time. I mean, it's remarkable how much of what we believe about the world depends on the way we are as observers. So, for example, in the case of the second law of thermodynamics, back from the 1860s even, people were worrying about the heat death of the universe. They were saying, well, you know, over time, the universe will just sort of run down and eventually everything will just be random heat. But that is an observer-dependent statement, because what to us now might look like, oh, those molecules are just doing random things, to a different kind of observer, for example, one who isn't computationally bounded, they would say that configuration of molecules, well, that's the future of this whole civilization that existed back, you know, billions of years ago that led to this kind of thing that we now think of as heat. So, and the same thing, I mean, if you think about our perception of space, that depends a lot on the way we are. Because, for example, you know, if I look around this room, it's, you know, a few tens of meters away everything I see is within tens of meters from me. And so light gets to me within microseconds, but it takes my brain milliseconds to respond to that. So as far as my perception is concerned, I'm just seeing the whole state of space at a succession of moments in time. But if, for example, you know, if you were using digital electronics instead of brainware, so to speak, that's a million times faster. It's no longer the case that it's so obvious that you see this kind of slice of space at successive moments in time. So our perception of things like the existence of space is a consequence of features of us, of the way that we are as observers. And my guess is that actually that eventually one will kick oneself because it'll be really obvious that there's some feature of the way we are as observers that makes it inevitable that we parse the structure of space as being three-dimensional, as opposed to just saying, well, we can, you know, the same information content existed if we were like a Turing machine head just moving around space in one dimension, but that's not the way that we parse it. So anyway, this is a little bit on things I've been thinking about physics. I thought I might mention some applications of all of this. I had sort of assumed when I was working on fundamental physics that things like this would have no application for 200 years. But it turns out that isn't true. And I was surprised to realize that it has all kinds of applications. And let me try and mention a couple. Let me see what... let's talk about math. So the question is, here's a kind of a weird question. The question is, what is the limit of math as time goes to infinity? So in the history of math so far, humans have published 3 or 4 million theorems in the literature of mathematics. The question is, if you keep going, what does math look like when you have 1 trillion theorems, eventually an infinite number of theorems? So you can imagine you start from some axiom, there's a simple axiom, and you can say, well, let's think about what consequences we can use that axiom to figure out equivalences between expressions. And we can eventually build up some whole pattern of equivalences, and then we can say, well, expression A is equivalent to expression B. We can find a path that goes from expression A to expression B, and that path is effectively the proof that expression A is equal to expression B. So we can think about mathematics as we can sort of building up from all these possible, from some set of axioms, we can kind of build up this network of theorems. And so, for example, let's take an example here. So we can take something like, so here we have the way these graphs get constructed is a little bit trickier when you have, there's an axiom at the beginning, and you're using that axiom to generate those other theorems. You can keep doing that. You can build up these complicated graphs of this. Let's do that, for example, for, what is this? This is probably semigroup theory. So this is the network that you get for the theorems of semigroup theory. And you can do that. Let's do that for, I think I have here, this is Boolean algebra. Is that, no, that's semigroups again. Where do I have Boolean algebra? Sorry. I think that's Boolean algebra. So with some axiom system for Boolean algebra, that's building up from the green axioms. You're building up those light blue theorems. You can keep going. This is you're building up more and more and more theorems of Boolean algebra. Most of those theorems are theorems nobody cares about. If you build up this whole entailment cone, it's kind of like in physics, you have light cones where you're having an event that leads to other events. In mathematics, you can have entailment cones where one theorem leads to you have one theorem and it leads to other theorems. And so here, there are a couple of theorems out of this big ball of possible theorems. There are a couple of theorems that people have given names to in the literature of Boolean algebra. You can keep going. You can find, you can eventually find, that doesn't have any notable theorems in it. But the actual, the proofs, these are just, the proofs again are just paths effectively within this giant sort of metamathematical object. And so you can think about this. You can think about sort of all kinds of features of this kind of giant graph that represents kind of the how theorems get derived from theorems in mathematics. Well, the limit of all of that is the same ruliad object. The limit of it, if you take all possible axiom systems, and you look at all possible derivations, the thing you will get is the same ruliad object. And so then the question is, well, in mathematics as we do it, there are particular axiom systems that we've chosen. What determines those axiom systems? You can do kind of empirical metamathematics. So, for example, that's the network of theorems in Euclid, starting from the axioms at the top, and I think the theorem that Euclid takes the most effort to prove is that there are 5 Platonic solids. But that's the graph of theorems. What's notable is that you can use things that people have done in proof-assistant systems and so on to look at kind of what is the structure of metamathematical space and you can do all kinds of things looking for sort of where are famous theorems of mathematics embedded in the structure of kind of mathematical space of all possible theorems. But what you end up with is essentially this as you do these kinds of things, you end up with a very low-level view of mathematics. And when you ask about something like the Pythagorean theorem, this is the derivation of the Pythagorean theorem in some proof-assistant system. It's about 7,000 intermediate lemmas. And what's underneath this? Underneath this is some set theory and all sorts of axioms. And the question is, how can you actually end up being able to do mathematics? How can you actually do derivations of the Pythagorean theorem without having to always grind your way down through 7,000 layers of intermediate lemmas, worrying about the definition of real numbers and all kinds of very low-level things like that? It is sort of one of the notable features of mathematics is that higher-level mathematics is possible. And what's interesting about that is surprisingly related to the fact that higher-level fluid mechanics is possible. It might not be the case that you could do fluid mechanics at the level of talking about velocity fields. It might be the case that every time you talk about a fluid, you have to start worrying about where does every individual molecule go. But it's an important fact that fluid mechanics is possible. I mean, there are cases where, in hypersonic flow or something like this, where you do have to worry about where the individual molecules go. But most of the time, you can think about fluid mechanics at this high level. So the same seems to be true of mathematics, that most of the time it's good enough to think about mathematics at this sort of higher level of where you're not having to sort of go all the way down to this axiomatic level. And that seems to be a feature of kind of human mathematical observers, that the way that we kind of parse this ruliad of all possible theorems and so on is one where we can, just as the way that we parse fluids and so on, is one where we can think about higher, sort of the continuum fluids, same kind of thing with mathematics. So there are all kinds of analogies between metamathematics and physics that you can start to see. So one of the more bizarre ones is what's the analog of a black hole in metamathematical space? So a black hole is what is a black hole sort of in physics? In the simplest case of a Schwarzschild black hole or whatever, it has the feature that it's a place where time stops. Every geodesic ends in finite time at the singularity. So in terms of our models, you can see that happening by this rewriting process simply doesn't have any more rewrites that it can do. That's what it looks like to have a singularity where time stops, a space-like singularity. So a black hole is in its simplest case, is a place where time stops, where every path has finite length. So what's the analog of that in metamathematics? Well, in metamathematics, those paths are proofs. So the question is, what is the situation where all proofs are in some sense of finite length? Well, a decidable theory in mathematics is something where all proofs are of bounded length. So sort of one of the big points of Gödel's theorem and idea of undecidability, sort of the limit of computational irreducibility, is that there exist in mathematics theorems that are in principle reachable from some given set of axioms, but the proof to reach them is arbitrarily long. So the statement that one has something where there is a finite length that you'll always, or bounded length at least, that you'll always be able to do the proof in a bounded length, that's like saying that time only runs for to a certain extent. And so that tells one that the decidable theories are the analog of black holes. And what's even more bizarre, and this is not fully worked out yet, but it seems that proof density is the analog of energy. Proof density in metamathematics is the analog of energy in physical space. And that what ends up happening is when you end up having in physical space, there are singularity theorems that say when you have enough energy momentum, it's inevitable that you will form a singularity in a black hole. That when you have enough proof density, it is inevitable that you will form a decidable theory. And so one of the other bizarre things then is that the future of the physical universe might be a bunch of black holes and so on. That might be the future of the metamathematical universe as well, that all theories have kind of become decidable theories. Well, another thing you can start thinking about is in the correspondence between physics and mathematics is that if you think about in physics, one of the big facts is that physics, the universe is fairly homogeneous. And you can have motion that goes from here to there. It's not obvious that motion is possible. So that seems like a bizarre claim. But if you think about, how can it be if this thing is in this place and I move it to that place, it's made of different atoms of space when it arrives at that other place. It's not obvious that you could be able to take this thing and just move it without change. And in fact, that's a thing you sort of have to derive. And so in mathematics, what is it like to move from one place in mathematical space to another? It's basically translating some mathematics that you're thinking about in terms of one axiom system, for example, let's say in terms of algebra, translating it into geometry, let's say. And so the idea of homogeneity in mathematical space would be the statement that sort of pure motion is possible, that most kinds of things that are stated in terms of one sort of approach to mathematics can be restated in terms of other approaches to mathematics. It kind of seems to be related to the dualities that exist that people discover in pure mathematics. That the way to think about those dualities is it's a homogeneity in mathematical space. So, okay, so just to mention, I mean, there's a bunch of other funky applications of all of this. Another one that I might mention is, let's see, we can talk about biology, we can talk about machine learning. I'll just talk briefly maybe about those. Let's see. Well, very briefly. Maybe yeah, okay. All right, this is so I was interested in kind of why does biological evolution work, which turns out to be closely related to all these things about multi-way systems and so on, and also closely related to machine learning and the question of why machine learning works. And so this is actually yet another cellular automaton. There are its rules on the left, and there's its behavior on the right. And kind of the concept here is this is an incredibly minimal model for biology, where the thing on the left you can think of as a tiny genome, and the thing on the right is the kind of phenotype, starts from that one red cell and then does its thing and dies out after some certain number of steps. So the question is, if we mutate that genome, we make single point mutations to that genome, and we ask the question, can we adaptively evolve this system so that it lives as long as possible? Well, these are kind of the waypoints in sort of in getting it to live longer and longer in this particular case. And we can kind of plot out, if we just keep trying different mutations, most of the time the mutations will be losers. They won't increase the lifetime, but sometimes there'll be sort of a breakthrough and the lifetime will go up. And so this is sort of a very minimal model for biology. And one of the things that is then interesting is that, okay, so that's that particular system, but there are many different, do I have a picture of that? Yeah, there are sort of many different things that can happen with the same underlying setup. There are many different ways that biology can sort of solve the problem of living a long time. And one thing you can do is to actually draw a multi-way graph that shows sort of all possible paths of evolution. So you're basically asking here you start off with just a null rule, and you're making point mutations to that null rule, always trying to every edge here corresponds to it's successful at living longer than it did before. So these are essentially the different branches here, like the different branches in the tree of life. They're different ways that organisms discovered how to be successful in the sense of living a long time here. So then, one of the things that one can think about is how does how does one think about kind of natural selection and fitness functions and all those kinds of things? And one of the things that is kind of fun is that you can make these multi-way graphs, you can make bigger ones. That's one for a slightly larger system. And the question is, there is a multi-way graph of what happens with all possible mutations. But the question is, with a particular fitness function, you will drive the system to a different part of the space. So, for example, if our fitness function, let's see, where is it? The different fitness functions, the end result is going to be fitness functions correspond to foliations of this structure. They correspond to essentially reference frames in relativity, which is a quite bizarre result. What happens, let me see if I can find you a good example of that. What's happening is that there's a graph of sort of all possible changes from mutations. But the question is, in what sequence are you actually, which things are the winners? How do you orient this graph? And the orientation of that graph depends on how you make these, you make these slices. And the basic point is the reason that evolution works is because the fitness function is essentially computationally much simpler than the underlying dynamics. The underlying dynamics, again, shows computational irreducibility. The fitness function is essentially a computationally bounded kind of thing. And the reason that biological evolution, in some sense, works and doesn't get stuck is that you have a computationally bounded fitness function that is being sort of run against these pieces of computational irreducibility. And what you realize is that often if you ask, if you look at some long-lived organisms, so to speak, one of the things that's notable, if you say, well, why did the organism live a long time? Well, in some cases, you might be able to give some kind of narrative story about why it did. But in many cases, it just, flaps around doing all kinds of computation and just dies out after 308 steps. And you can't really give an explanation of why. And so what biology seems to do is it finds these kinds of lumps of irreducible computation that it successfully manages to get to satisfy the sort of the constraints that correspond to fitness functions. Okay, so that's sort of a picture of sort of foundations of biology there, and you can do all sorts of fun things like I was interested recently in kind of the theory of medicine, a foundational theory of medicine, where you can ask questions like, well, if you imagine that you have sort of a healthy organism that's evolved to do what it does, then you poke it in some way, it will behave differently. Then you try and fix that by sort of treating the organism. To what extent can you do that? So there's a fun story about that. But just to talk about machine learning for a second, the same kinds of things happen there. So this is a typical kind of neural net. You've got some input at the top. You've got a bunch of neural net weights that were found, and this thing computes that function over there on the right. Okay, so that's sort of standard neural net stuff. And it's kind of complicated. You can look at as a function, what are the activations doing as a function of the input and so on. It's pretty complicated. One of the problems with neural nets is very hard to visualize what's going on. So one thing one can do is to make it a bit simpler, put the things on a grid. You can still learn a function like that. You can even go further than that. You can say, well, let me not just put the things on a grid, but let me have the activations be discrete. And let me just have the thing use a cellular automaton again. And just say that at every position in this grid, you're either running one rule or another rule. So then you can ask, well, how do I, for example, let's say that I want to machine learn how to live for 50 steps and then die out. This is making a series of mutations, essentially changing a bunch of weights to get to the point where this thing lives for 50 steps and then dies out. And so that, and you can compute fitness functions or loss functions, things like this for this. What is interesting here is when you ask, well, how did it manage to live for 50 steps and then die out? Some of the time, it's very mechanistically explainable what's going on, but a lot of the time it is not. It's kind of a piece of irreducible computation that just happens to work. Well, what seems to be the case is that this is the general story of machine learning, and you can do more complicated cases and look at more elaborate kinds of things, but the end result seems to be that the story of machine learning is a story of kind of finding lumps of irreducible computation that happen to be able to satisfy the things that you are trying to do with machine learning. So, for example, my analogy to this would be if your goal is to build a wall, one way you can do that is by making nicely shaped bricks and doing the careful engineering of putting every brick in the right place. Another thing you can do is just look at the random rocks that are lying around on the ground and try and fit in rocks in such a way that they more or less fit together, and then you can build a stone wall that way. I think that second thing is basically what's going on in machine learning, and that what's happening is you're finding these sort of lumps of irreducible computation that happen to fit together well enough to be able to achieve the fitness function, the objective, the minimizing the loss function, whatever, for the machine learning that you're trying to do. So that kind of has a bunch of consequences in terms of thinking about what is possible with LLMs and so on and not. And it's kind of quickly segues into my day job, because we happen to make the sort of the big idea of my kind of day job life for the last 4 decades has been building our Wolfram language, computational language, where the sort of the objective of it is to sort of take what's computationally possible and make a bridge between that and the kinds of ways that we think about things. So kind of the idea of the language is to be able to have sort of a computational representation for kind of everything in the world. And and so we're sort of dealing with, I don't know, you have a representation, you might have you would have a representation of something like, Providence as let's see if it decides that that's Providence, a city. Okay, good. You might say, what's the population of that? But this is now an entity, so we can say, we're dealing with sort of computations about anything. So this, we might say, I don't know, make let's say something like this. Make just a map. But I mean, the whole idea here is to have a language that can sort of represent things in the world computationally. So the kind of the thing to realize is there's sort of the overall goal is to have kind of a way of representing things computationally that provides sort of a formalism for thinking about the world computationally. So it's kind of, I see it as being sort of a step beyond what was done 500 years ago or so now with mathematical notation, where people kind of invented, plus signs and equal signs and so on, which kind of streamlined the treatment of mathematics, let one develop things like algebra and calculus and so on, and eventually gives one kind of the mathematical sciences. Sort of the different problem is, if you use computation as a foundation, you have to sort of make a humanized kind of notation for computation, and that's what lets you build kind of the computational X for all X fields. That's sort of the analog of the mathematical sciences. It's kind of the computational X fields, and that's kind of what I spent the last 4 decades trying to do. But the relationship of this to kind of the world of machine learning and so on is this kind of building in a different direction. I mean, LLMs and so on do a very good job at providing kind of a linguistic interface to things, and do a good job of things where we humans they sort of emulate what we humans can easily do in our minds, possibly because their architecture is pretty similar to ours. There has been this different direction, which is building up formal kinds of things. That is what one is dealing with in sort of computation and in the kinds of things I was talking about with computational irreducibility and all those kinds of things. And so we have these kind of 2 directions of this sort of humanized linguistic interface and this kind of direction of building the sort of tower of computation. And so the thing that I've been involved with for a long time is sort of building that tower of computation. It's pretty neat that these days one can bring those things together. There's a cool thing which I'm not going to particularly demo, but the notebook assistant for Wolfram Language is now pretty nice, that allows one to sort of say something surprisingly vague here, and it will synthesize Wolfram Language code that gives one at least a good first step in taking one's idea and kind of representing it computationally. Anyway, I guess I've at least had fun for the last few decades sort of alternating between developing this kind of technology and doing some of the basic science that I've talked to you about. And I think one of the there is much to do in this basic science, and much that becomes possible with kind of using the sort of computational language ideas that we've developed. I kind of like to think in terms of physics that about 100 years ago, many things happened in physics. I'm pretty sure that we have the seeds of what's necessary to have the sort of the next very fertile period of physics, sort of about 100 years later. And we've got a long way to go, but I've tried to tell you about a few of the early parts of that. So I should stop there. Thanks very much. Well, I'm happy to try and answer questions, or yes, please. yes, then other people can hear you.
Thank you for the talk. I was wondering about your discussion with the fitness function. You sort of are hitting at the point of like the structure-function relationship in biology. And I was wondering, how much do you think the language of inverse problems is useful in thinking about, say, what kind of regularization do you put on the space of rules or something like that, that to give you a certain function or something like that?
Well, okay, so the question is, I mean, when you're looking at, okay, what I've done in thinking about biology is in a sense very dumb. I'm just making point mutations on this rule. And you might have thought, okay, so I started that project actually in the mid-1980s, and I thought that something like this might work. And at that time, I thought, as you are thinking, that you have to be very clever and figure out some careful way to do this. I tried to do it in sort of a dumb way back then, and it didn't work. I retried it last year with one important intuitional change, which was that I know that machine learning works. And the big discovery of machine learning that happened in 2011 is if you bash a neural net hard enough, it will learn stuff. That wasn't obvious. Nobody knew that. I mean, I played around with neural nets in the 1980s. I couldn't get them to do anything interesting. I had sort of given up hope that they would do anything interesting. So the surprising fact is, if you take even a very dumb thing where you're just making these point mutations, you can successfully evolve to satisfy lots of fitness functions. Now, an interesting question is, what fitness functions can you actually, can you successfully kind of get to? What things can you learn? It's like, what things can you learn in machine learning? What biological evolution, fitness functions can you reach? I don't know the answer to that. That question is very similar to questions about what are reasonable reference frames to use in general relativity and so on. There's a whole bunch of questions that are sort of characterizing what types of things you might use as the objective function. And I think it is a very interesting thing to try and figure out sort of a theory. I have tried to develop the thing I call observer theory, which is an attempt to characterize the kinds of things that observers can do. So, for example, in computation theory, we have things like Turing machines, which are sort of minimal models of what computational systems can do. There's an analogous question of what are minimal models of what observers can do. And the key thing that observers do is they equivalence things. Whereas computation goes from one state, makes another state, makes another one. Observers take, this whole array of pixels that I'm seeing right now, and I conclude something that is much filtered relative to that raw array of pixels. And so the question then is to characterize those kinds of equivalence functions. And I think it's a super interesting thing. I don't know how to do it entirely. Yes.
Yeah. Thank you for the talk. So with your theory of hypergraphs, I understand that ideally every physical property will emerge, space, matter, energy, from these graphs. And I'm sorry if you already answered this, but I'm wondering about the actual ontology of the graph itself, the nodes and the edges. So what exactly are they, and do they correspond to actual physical
They're the
things?
stuff the universe is made of. And so that's not a kind of thing that we've had before, so to speak. So if you're saying, can I pick up an atom of space? What would you pick it up with, so to speak? I mean, in other words, it's the lowest level representation. It's the sort of ultimate data structure of the universe. So there's not really a way to, it's something very unfamiliar in terms of the things we are familiar with, like space, are very, big compared to it. So to give you an example of how to think about it. So one question you might ask is, in these models, it's like, there's a person who worked for me for a long time who was working on an earlier version of this physics project, and he would tell people he's working on fundamental physics, and people would always ask him, when are you going to invent warp drive? And so, a reasonable question is, if you have a fundamental theory of physics, is it possible to go faster than light? It's a reasonable thing you might ask. Well, in this theory, you can actually address that question. So we have these causal graphs, and, well, okay, let me give an analogy again. I'm going to use a thermodynamic analogy again. In this room, there are a bunch of molecules that are going at the speed of, roughly the speed of sound, but they only go a micron or so before they hit another molecule. And the time for a typical, perturbation here to propagate, if I let some chemical out here, the time for it to diffuse to the other side of the room is long. It's the diffusion time. But if you were able to be very clever, kind of a Maxwell's demon-like thing, and figure out exactly which molecule to hitch a ride on going across the room, you get across the room at the speed of sound. Okay, so it turns out the same kind of thing is possible in physical space. If you look at this causal graph, if you knew exactly which atom of space to hitch a ride on, you could get from one place to another faster than the speed of light. The problem is that what's the U in this case? Because the U is some big thing that's, 10 to the 100 atoms of space or something. But the thing that, first of all, you have to have very high computation capabilities to know which atom of space to jump on next, so to speak. But the main problem is it doesn't get to be a U that gets through at sort of faster than light, because you can't stuff that whole 10 to the 100, atoms of space thing through this, just like you can't piggyback on individual molecules. You as a large organism can't piggyback on individual molecules to go across the room. So it's kind of that's a little bit of an example of kind of the what is the relationship between what we perceive and what's actually there underneath. But the kind of the concept is there's people sometimes say, well, if it's a computational system, what computer is it running on? That's really the wrong question, because it's like asking, if you say there are differential equations that govern the motion of the Earth around the sun, you could say, well, where's the Mathematica code that's running those differential equations? That's sort of not the point. The point is the equations are a model that are a way of representing how the universe works. And this is the same type of thing. This is a model of how the universe works. It's a model which attempts to bridge from sort of what the universe is actually doing to something that we can understand with our minds. I would not claim that hypergraphs are the only way to represent this model, that we already know of some other, I think, much more obscure ways to represent this kind of model. That's just a representation for purposes of humanizing sort of what's actually going on.
Thank you.
Sure.
Wow, that was a lot. Thank you for your talk. This is really interesting. You said something like mass is the density of connections.
Not quite, but not quite. It's mass is slightly tricky. Mass is energy is essentially the density of activity in the network, and it is the, as you look at these causal edges, you can say the density of causal edges going through space-like hypersurfaces corresponds to energy. The mass is roughly, and I need to find a better way to say this, but it's roughly the extent to which kind of causality remains localized, as opposed to kind of within one of these space-like hypersurfaces. It's the extent to which the kind of chain of causality remains localized to one part of the space-like hypersurface instead of sort of spreading out elsewhere. And that's kind of intuitively obvious, because a massless particle is one that propagates at the speed of light. And these causal edges are precisely the, you can think of them as light-like edges. And so essentially it's saying that when you have a massless particle, it's moving across the space-like hypersurface. This is very, very vague and
So, but it's something like you got a number of these atoms of space, and if there's a lot of them, that's a lot of mass that hang out together. Something like that.
Unfortunately, the hang out together is hard to define. Because,
I see. Okay.
Because if you think about it, all you know is the connectivity of the network.
Right.
So the network, if the network just saying there's more edges doesn't really tell you a lot. What matters is things like the dimensionality of the space, which is determined by this thing that's a little bit more difficult to visualize, because it's not just the number of connections, it's the growth rate of how far you get when you go out a certain number of connections.
Okay, so the question really is, can you understand inertia easily with this model? Or is it tricky? It's something to think about.
Let's see. What do we mean by inertia? We mean, the answer is I can't give you a quick version of that. I mean, I can tell you one thing that I realized recently, which is kind of obvious, which is it really matters that we're not massless. If we were massless observers, we would observe the universe very differently. And in particular, time would not pass. And, every photon coming from the cosmic microwave background thinks no time has passed since the beginning of the universe at the moment when it's, captured in a detector. And I think it is important, one of the things that I strongly suspect is the case is that, and many of these things will end up being kind of obvious, that the way that the reason we get the laws of physics we get is because we are observers like we are, and the features of what we're like the fact that we are not massless, is, I think, important to getting the laws of physics that we get. And there'll be a sequence of these things that are, because we are the way we are, we have laws of physics we have. But in terms of, I should have a good answer to this. I don't have a good answer.
Well, thank you. No, thank you. Lastly, can we learn more about this reading? Where can we look to read about this?
Yeah,
if we want to learn
there's all sorts of stuff about this. If you go, there's a wolframphysics.org.
Okay.
There's a collection of
Great.
things.
Thank
but
you.
there's a fair amount that's been written by, not. I would say that there has been probably more on the connection. Okay, so one of the things that's happened is connections to other approaches to mathematical physics. So, you might have thought if this model is right, all other models are wrong, but that's really not the way it's playing out. What's turning out to be the case is that a lot of other models like causal set theory, like spin networks, perhaps like string theory, although that's more speculative, end up being limits of these models. So this is a low-level infrastructure from which these other things are kind of higher-level structures. And I would say there's been more done on the formal aspects of these things and on the relations with higher category theory and who knows what else. I would really like there to be more work done on things like the experimental implications of these models, because I think there's a lot of, I have been hoping that other people would do this, and I have just about decided I have to do this myself. So and actually one interesting thing about doing this oneself in modern times is that this is a place where I'm really using an LLM as a research collaborator, because basically what I want to find, I don't want to be caught in the same catch that people were caught with Brownian motion. Brownian motion was discovered in 1827. And throughout Boltzmann's life, for example, Brownian motion was known. And yet Boltzmann had no idea that molecules existed. But if he'd actually gone and looked at the botany literature, he would have discovered that there was this phenomenon of Brownian motion, and he would have had evidence that molecules exist. So of the million physics papers that are out there, the question is, where are the thematically relevant physics experiments that have already been done, which often people didn't report very strongly because they were too weird. And yet they're out there, and can one mine those things? And so that's been my recent use for LLMs, which has been working okay, I would say. It's I think there's a lot of, well, I would say that one of the other pieces of what has to be done for this project is rebuilding things like differential geometry from hypergraphs, because in differential geometry you assume that the lowest level object is a manifold, which is ultimately like Euclidean space. Here, the ultimate model is not Euclidean space. And so we've been trying to build what we call infrageometry, which is a rebuilding of geometry without those assumptions. And so the goal is to get to the level of being, we've got a certain distance, but we want to be able to really describe what the Riemann tensor in 3.01 dimensional space is like, about which almost nothing, basically nothing is known. There is no mathematical literature on that. And so there's quite a heavy lift on that kind of practical theoretical side, as well as on the side of kind of experimental implications. And I'm sort of hopeful that there is some very nifty experiment that will be kind of like the Brownian motion of this case, where you'll be able to see evidence. I mean, Einstein was really lucky with general relativity, because one of his predictions was that light would be bent a factor of 2 more going around the sun than in Newtonian gravity. And that was a factor of 2. It wasn't something that depended on the cosmological constant. It wasn't something that was parameter dependent. And I might mention, since I know there was some quantum theming to this whole thing, I might mention one of my hopes about an experimental implication of all this stuff is that quantum computing is a fine thing that I've actually thought about since the beginning of the 80s. I've always thought it was not going to work. And now I have a kind of a better view of my view of what's going to work or not work, which is that, in these models, it's pretty easy to see that you can have sort of inside the quantum process, you can have all these different threads of computation going on. That seems really good. It seems like you're going to get all these parallel things happening. The problem is we humans believe that there's a definite sequence of things that happen. So we have to knit together those threads of quantum possibility into some single outcome, which is, in the standard formulas of quantum mechanics, is just you do a measurement. But quantum mechanics doesn't talk about how that measurement happens. In our models, we can begin to talk about how that happens, how you knit together these different threads of sort of quantum history. And my guess is that when we do this right, that something like Shor's algorithm will just not work. That is, that the effort to knit together the threads will be greater than the effort than what you save by being able to have these parallel things happening. And so I don't know if it's really right. The question is, how would you see that experimentally? One way you'd see it is probably that there are these weird noise floors and weird decoherence times and so on. So my current hope or guess is that you go talk to the quantum computing companies and things like that, and the typical front office version of the story is, if only we could do the engineering better, we will be able to make the quantum computer work. And my analogy for this is, imagine you were talking to telescope makers, and they're telling you, we're going to be able to see grains of sand on the moon. We just have to make the mirror, more precise. We have to polish the mirror better. Well, of course that won't work because of diffraction, because there's a fundamental physical phenomenon. And my guess is that there is similarly a fundamental physical phenomenon that shows up in the quantum case. And if we are really lucky, okay, so I didn't mention another thing. In our models, just as there's a speed of light in physical space, there's a maximum entanglement speed in branchial space, which is kind of the analog in branchial space of maximum propagation speed in physical space. And so if we're super lucky, it will be the case that the engineering has been done well enough that existing quantum computers can actually measure the maximum entanglement speed. I think this is somewhat wishful thinking, and it probably is off by 50 orders of magnitude, but if we're really lucky, something like that will be true. If we can measure the maximum entanglement speed, that is related by Planck units and things to the elementary length, and then we've nailed down all parameters in this model. But anyway, that's my, so I keep on telling people in the quantum computing business that the most interesting thing is what doesn't work, not in other words, that people should study the noise, because the noise is actually where there's going to be a major piece of physics. And it has been the case. I will say that, in a lot of things I've studied, people had observed things like the Rule 30 phenomenon that I talked about earlier. People had observed things like that, but they'd always just said, that's noise. That's something we don't care about. And it turns out that's actually the story. And so I think, I'm guessing the same thing will happen with quantum computing. Anyway, just my prejudice. So I see various questions.
Yeah, so you mentioned that the perception of three spatial dimensions is not an ontological reality, but has to do with observers like us. And my question was, is there anything that can be said about the true number of spatial dimensions, if that's even a thing, or is it always dependent on the kind of computational capacity of some observer? And does that range from 0 to infinity? Is there anything that can be said about it?
Yeah, I think in the ruliad, all possible, you can parse the ruliad to get any spatial dimension you want. So the question is, why do observers like us parse it in such a way that it is perceived as three spatial dimensions? I don't know the answer to that. I would love to know the answer to that. I don't know. I will say one thing, another perhaps intuitionally useful thing about observers. So here's another weird thing. So in quantum mechanics, one of the questions, okay, so in these models, kind of what ends up being sort of the story of quantum mechanics is how do branching minds perceive branching universes? And so one of the questions in quantum mechanics is, why is there randomness in quantum mechanics? We have essentially a completely deterministic model. Why does anything seem random in quantum mechanics? Well, here's an analog of that in physical space. So we have laws of physics, and we think they're the same everywhere in the universe, but there are particulars of the planet that we're on that cause us to see the particular night sky we see. But we all agree about what the night sky looks like because we're all on the same planet. So now in branchial space, there's the same kind of story, that observers at different places in branchial space will observe different things happening. But the issue is, if all of us are incredibly nearby in branchial space, we will agree about what happened, even though what happened is determined by where we happen to be, which is not a determined thing. That's an arbitrary thing. There's no theory that says we will be on this planet rather than some other planet at some other place in the universe. So in any case, there's much to be said about that in that direction. We should probably go on to another. Yeah, I lost the thread because you had asked about. Right. So the question is, what this kind of flock of observers in the ruliad, and what characteristics of that flock of observers one can deduce. And I kind of suspect, another bizarre claim, is that it is important to have many similar observers. You won't have the same kinds of properties unless you have many similar observers. Having many similar observers ends up being something related, for example, for us to biology. So there are these sort of collection of connections. Okay, I'll give you one other very bizarre connection. So in the ruliad, one can think about different points in the ruliad as corresponding to different assumptions about what the fundamental rule of the universe is. So how to think about the universe as following a particular rule. So you can think about every mind is at a particular place in the ruliad. Every mind has a different way of describing how the universe works. Minds that are nearby, some minds are nearby, like humans with similar educations or something are probably nearby. The cats and dogs are further away. The weather or something also has some whole complicated mind-like dynamics, but it's much further away in rulial space. And so here's a very bizarre thought, which is if you are thinking about sort of communicating across rulial space, you need some carrier of pure motion in rulial space. You need a thing which doesn't change its character as it moves through rulial space from one mind to another. And so, like for human minds or whatever, it's like we all have, all kinds of nerve firings happening in our brains. And when some concept is mentioned, each of us will have a different detailed pattern of nerve firings in our brains. But yet, we package those firings up into a word, like cat or something. And then we can transmit that word to another mind, which can successfully unpack it. So in some very bizarre sense, I think concepts are the analog in rulial space of particles in physical space, which is a very bizarre another one of these very bizarre kind of connections between things. But anyway, I think I think some of these kinds of things I think are relevant to this question, but I don't exactly know how yet. Please.
Thank you so much for the talk. By some good coincidence, you started addressing my question in that last discussion anyway, but I want to ask, you talked a while ago about classical randomness having something to do with the computational limit, and then you just started mentioning randomness in quantum mechanics. So I want to understand how that could be related to, in something that seems somewhat deterministic, to satisfying something like a Bell inequality. How do we get the quantum mechanics that we sort of see from this sort of underlying structure?
Well, the whole story of Bell's inequality and so on becomes, that's all very easy to derive. Once you have this notion of branchial space and so on, all the sort of derivations of and standard quantum mechanics are kind of pretty easily convertible to talking about multi-way graphs. At an intuitive level, this thing that I was mentioning of the reason you get randomness is because you sort of don't know where you are in branchial space. It's not, in other words, everything is determined, but knowing effectively what your coordinates were in that sort of space of possibilities is something that you can't determine. And that's something which, therefore, there's no derivation of that. So you have to consider that random. It's randomness of a slightly different origin from what happens in something like Rule 30, where you know the initial condition, and then you're generating randomness computationally. I think that second generation of randomness is also very relevant. It's super relevant in things like, so the structure of the vacuum and things like that. I think, again, not properly worked out. So I can't give the very short answer because I haven't worked out the much longer answer. I will say that okay, so a recent realization. Long ago, I worked on Feynman diagrams. As was mentioned, I knew Dick Feynman quite well. And one of the things that Dick Feynman would always say when I was working on Feynman diagrams, he says, those Feynman diagram things are kind of stupid. There's got to be a better way to work out how things work in quantum field theory. Well, we haven't figured that out for the last 50 years or something. But the main realization that I had recently was I thought to think about things like Feynman diagrams and quantum field theory, I would need to understand again what particles are. But then I realized quantum field theory does not understand what particles are. In quantum field theory, you just are, you look at the initial, bunch of plane waves in the initial state, you have some big S matrix, and out comes some final plane waves. And what's a particle? Well, it's certainly not a plane, it's not a real sort of, a proton is not the structure of a proton is not described by a plane wave, so to speak. That's just a way of representing sort of the asymptotic things that are coming in. So I realized, so the question is sort of what are Feynman diagrams? And I realized that these causal graphs that we have basically are the analog of Feynman diagrams. Feynman diagrams are the interactions in Feynman diagrams. The vertices in Feynman diagrams are like events, and the lines in Feynman diagrams are like causal edges. And the Feynman diagram represents the causal relationship between those interactions. And it turns out it's looking very promising to be able to derive sort of a lower level version of Feynman diagrams where, the most recent thing is you get, in these causal graphs, you can get loops, and there's a notion you can do things like renormalization to deal with getting rid of infinite sequences of loops and so on, and it all seems very, very analogous. I'm not sure that's entirely responsive to your question, but it's that we're sort of slowly trying to make connections between what we figured out and the things that are already known in physics. And I thought the Feynman diagram thing was going to be pretty far away, but it's actually looking much closer now. I think maybe just please. I'll try and repeat a question if I can hear it.
It's kind of a long question.
That's all right. I can hear you fine. I don't know about anybody else, but okay.
I guess
fine.
for everybody else in the audience.
Right.
Thank you for the talk. Huge fan of the software. It's been helpful in research because I'm a high energy theorist. Okay, so obviously this hypergraph, basic hypergraph structure that you've presented is pretty ambitious. It's recovering general relativity. It's recovering quantum mechanics. As you're alluding to, you're looking forward to maybe recovering Feynman diagrams and parts of quantum field theory. How well does it play with current, other things that try to do that? Like, obviously, the example that I'm thinking of is string theory. Could it maybe recover the world sheet for a string? If that's too distasteful, maybe, even in loop quantum gravity, could it recover spin foams in loop quantum gravity? Right. Do you see this as just like a formalism, or do you see this as like something that really underlines everything?
I think it's the machine code for all these other things. So, for example, causal, what's it called? What is it called? The not spin networks, but the other formalism where you're putting random points in space-time. Causal, what is it called? Causal, I forget what it's called. Has the word causal in it, but it's one of the formalisms that people have tried where you're putting random points in space-time and you're just talking about their causal relationships. It's been very confusing in that field forever why you get Lorentz invariance. In what those people have done, they are basically putting points in space-time at random. In our models, we actually can say where the points will be in space-time, and they will be in places which lead to Lorentz invariance. So that's a case where there's a bunch of formalism that's been worked out based on random points in space-time, which actually has some useful consequences for what we're doing, but yet our model can say that the points are not completely random, just uniformly distributed, but distributed in some particular way. So that's that case. In the case of spin networks, there's again a bunch of things where you're essentially aggregating pieces of this hypergraph to represent the things that correspond to spins. And that looks pretty promising. I would say I don't think. Some other people think that they've more or less worked out that correspondence. I think there's still some I's to dot and T's to cross in the correspondence with spin networks. In terms of string theory, that one's a little bit more distant, and I've encouraged many friends of mine who do string theory to try and figure this out. And I have to say that they keep on telling me, oh, I'm not really doing string theory anymore. So but here's what I think might happen. So one of the things that has to happen in our models is in this hypergraph, we have to both get, okay, so in typical gauge theory, you have sort of the base, you're thinking about things as a fiber bundle. So you have a base space and you have fibers. So our hypergraph has to contain both the base space and the fibers. So we have toy models where you can see how those unravel. So you can see what aspects of the hypergraph correspond to the base space, what aspects correspond to the fibers. But we kind of have to work out, I mean, we have to work out how that limit works to understand sort of the things that string theory says about, actually there's a thought about how you would get sort of a simplified version of our models, which would happen to work when you had a kind of a hypergraph structure that was of a particular form that might correspond to a particular, a limited set of possible dimensions, for example. How that works in detail, we don't know. But it is my strong guess that something like string theory is a limit of our models. That is, it's and possibly an interesting limit, possibly not an interesting limit. I don't know. I think, I think the way to, that's probably all that can be said right now. I mean, I for a while I had this sort of guess, which was more something that I thought was funny to think might be true, and I don't think is true, but it was kind of a fun thought that the actual limit would correspond to, so usually we have these hypergraphs, but you can imagine also character strings, just A's and B's and so on, and do rewritings of character strings. And so for a while I kind of had this physics pun, which was maybe string theory is the limit of string rewriting. But I don't think that's actually true, even though it would be a lot of fun if it was true. But it doesn't. For a while, it looked like one might be able to get world sheets and things from thinking about actual strings and the rewriting of strings. But I don't think that's quite right. Even though it would have been really, really amusing if it had been turned out to be true. But so the concept in general is, it's hard work to connect these formalisms. But so far, whenever we've been able to make those connections, they've worked out pretty well. And one thing to say about what we're trying to do is, in general, you make a model of something, you look at the way the thing actually works. Every so often you find some glitch where you say, my model, I have to tweak my model somehow. So far, in 5 years or so, we're at 0 tweaks. That is, there's nothing, the structure of the model is what it is. And, it might turn out not to be true. I'll be amazed if it isn't true. It's somehow the level of elegance and the number of things that sort of fall out as obvious. I mean, just all these different kinds of things that have been mysterious. Like, why is the relativistic transformation for energy momentum the same as the relativistic transformation for space and time? It's obvious in these models, but it's never been obvious before. And they're just, a raft of things that become obvious, which I consider very encouraging. But there's still a lot of hard work to be done in actually both setting up the formalism for this whole infrageometry stack and figuring out experimental implications. And, the really cool thing that might happen is, somewhere mining some paper from 1975 or something, there may be some effect that one can say this is something which, if it had been interpreted correctly, would have been seen as a dimension fluctuation or something. I think the other one, for example, this dark matter thing, that is so, it's just, there's, that involves, for this sort of way of making general relativity calculations in traditional general relativity, one starts off with the continuum Einstein equations, you then discretize them, and then, work out things from that. In these models, you're starting from the discrete system and then working upwards to get something that's in a continuum approximation. So people have been using our stuff to do sort of actual Einstein equation simulations, for them, if there's a deviation between what you get from the continuum case and what you get with our models, it's kind of a lose, it's a bad thing. For us, if there's such a deviation, it's fantastic, because it means there's a way to actually see the discreteness of space somehow in some effect. And that there are some slight indications that in black hole mergers, you get different, there are some detailed differences maybe in black hole mergers that you would expect from these models, but it's still not well tied down. Yeah.
Thank you.
Sure.
So my question is that you said that time can be described as the idea of progressive computations from one state to another. So for us, computationally bound people, is it true that within the particular entanglement within which the computations are going on forever, is it true that no matter what the starting point is, maybe for us, the final time point is not the same, but then for someone who's not computationally bound, it's like everything's going to a same point?
Okay, I think I understand the question. Let me see if I understand the question. So one of the tricky things is, let's say you have a definite rule for how the universe works. Let's say you have this ruliad object, which is the limit of all these, applying all these rules. You could just say the ruliad is a timeless thing. It's just the whole thing already exists. It's just there. It's a thing. So there's no notion. You might say then, well, what's the notion of time? If you've got this whole object that represents the whole history of everything that happens, how then is there a thing like time? And what you realize is that there's sort of different ways to think about it. You can either think about the universe as sort of being constructed progressively, or you can think about the whole universe is already defined, but we as computationally bounded observers can only explore that universe sort of one step at a time. So it's kind of I think, I'm not sure if that's addressing your question. Your question was, go ahead.
What I'm trying to say is like, say, for example, there are different people who start from different initial conditions, but the final, like the point that they have to reach, it's all the same. Like everyone reaches the same point, but following different trajectories. But to them, it might seem like the path is different. So,
I see. I mean, so I think, in quantum mechanics, that's, so one of the tricky things, I think, okay, one feature is that we don't have quantum brains, basically. We could have brains that didn't just follow one path of experience, but followed many different paths at the same time. It is a fundamental feature of us that we don't have that. In fact, I just think I figured out why. Here's a funny fact. So animals have brains, plants do not. Animals move around. Animals seem to have produced brains because they need to know where to go next. And one feature of an animal that's trying to figure out where to go next is the whole animal has to go to the same place. It isn't that it can sort of develop a multi-way view of where it goes. And so in a sense, one feature of brains seems to be that our brains are very sort of carefully set up to take in all the sensory data and then conclude one definite thing to do next. And my current theory, as of a few days ago, is that what originated that was the fact that we could have brains that had many different threads of experience happening at the same time. I don't think there's anything sort of biologically impossible about that. We just don't have that. As a society, we have that. We have, biology has many different organisms, and we have many different brains that are doing different things. But within our brain, what seems to be happening is it's all concentrated down into this one sort of decide what to do next type thing. So this question of whether you could have something where two different, so where you kind of have two different threads of experience, which are, I think the answer to that is yes, you can have that. And that's sort of what happens in quantum mechanics. But in these models, you can't, it's like what I was describing about going faster than light. You kind of can't get a mind-like thing into that single thread of, that single thread of history is kind of too small to be able to have a whole mind-like thing connected to that single thread. I think that's the way to think about it. It's a good question. I actually am not sure that I don't think I've thought about that question as such before. Maybe I have. I wrote this little essay about the notion of time maybe 6 months ago, which has a section about quantum mechanics, and it might be in there, or it might be something that I haven't thought about before. I'm not sure. Please.
Can I give a question? Can I give?
Whoever, yeah, just you've got the microphone, so use it. Yes.
So I have a question. So for this hypergraph, let's assume that your description is a complete description of the universe. Let's assume that we figure everything out, that it's an accurate description. From what you understand currently, how many variables are there in the initial condition? We have the description of how the hypergraph changes through time.
Yeah, right.
Are there many other variables you would suspect that would be part of the initial condition in some sense?
Okay, this is another can of worms, because in this ruliad object, we imagine that we're starting from all possible initial conditions. And so that means what we've got is, I have to say, I think that this, so what we're, as observers, we are sort of sampling one piece of what's happening in the ruliad. But it isn't the case. You might have said there's lots of information. Even if we know the rule, there's still lots of additional information to put in about the initial conditions. What's being claimed is that that's not the case. That in a sense we've got that the whole, all possible rules and all possible initial conditions are being put in there. And what we observe about the universe is kind of the structure that comes about from the progression from initial conditions through rules and so on. So this is, I will say again that this is difficult stuff. I don't think I have as my basic answer is I think there is no specification of initial conditions because you're starting from all of them. And that means if you want to have, okay, so it's a little bit similar to what happens in fluid dynamics, where you can say you can have this kind of molecule or that kind of molecule, but all of them will give the Navier-Stokes equations. This is a case where you can have this particular form of rule or that particular form of rule, but on a large scale, you will observe phenomena which seem the same. I mean, this is that's my first cut of an answer to that. Complicated.
That a group of observers would observe somewhere what we see, in other words.
Yes, that observers like us inevitably observe the kinds of things we observe. And if you were to imagine an observer utterly different from us, the laws of physics won't be even close to the same. Their implied laws of physics from their perception will be completely different. One of the things that's sort of interesting about this whole effort is that, one is quickly, a lot of these questions quickly segue into sort of old chestnut questions in philosophy, which one can actually have useful things to say about now. Like one of the things that's sort of a very old chestnut in philosophy is, why does the universe exist? Is it inevitable that the universe exists? In these models, the existence of the ruliad is a necessary thing. Once you have the definition of computation, it is inevitable that the ruliad is a thing. And so you actually can make sort of scientific arguments about why it's inevitable that the universe exists. What's less obvious is that observers like us will exist. That's something you have to derive. But the existence of the universe is something that is sort of, in these models, is a necessary thing. Anyway, we're segueing it. Yes, please. Interesting question. I mean, the fact that, even for a piece of digital electronics that runs at, gigahertz speeds, it's the fact that you're sucking in all those photons from this scene and kind of making them, sort of integrating them into this thing that's the state of space at a particular time is, I don't know. It's a reasonable question to try and think through how one would perceive the universe if one was even able to do things a million times faster than we do. I don't know. It's the same type of thing. If you are in thermodynamics, if you're a very successful Maxwell's demon level creature, you will not say that there's randomness happening in these molecules. You'll just say these molecules are going where they go. It's not, they all seem to be going where they should be going. They're not going randomly, so to speak. And I think I have not thought this through, and it's a good, I have this suspicion, the sort of meta-intuition that when we finally figure out the argument for why observers like us have to perceive three-dimensional space, there will be something really obvious and something that, I realized only fairly recently that the fact that we're not massless is important, which is something really obvious. And the fact that this point that, the existence of objects in the world, which is something very fundamental to the way we perceive the world, is not completely obvious. If we think of things in fluid dynamics, for example, the existence of discrete objects with a definite identity is not nearly as obvious. But so I don't know the answer. It's a good thing to ask about. I don't know the answer.
I wanted to ask about so we have these pockets of decidability. When we go back to our physical space, how can we think of the rest of it that's undecidable? And then I guess another thing is if we were, let's say, a photon, or we're able to have access to your entire graph, we wouldn't have any notions of undecidability or decidability. Is that right?
That's a good question. I mean, so photons don't really have much notion of time. And so I think the notion of, it's a good question, how much computation is going on in a photon? And maybe the answer is that that the fact that no time passes for a photon is a sign that sort of no computation is happening in it. But I don't know, to this question of what, it's sort of fundamental to the way that, the fact that time, first point is the sort of invariant notion of time. There are many different kinds of things that do what they do in the universe. Our brains, fluid dynamics, et cetera, et cetera, et cetera. But somehow there is an invariant notion of time. So back long ago, people didn't know that there was an invariant notion of temperature. People thought, the temperature as applied to a block of iron worked differently than temperature as applied to this, worked differently according to that. And then it was realized that there was an absolute scale of temperature that was, that could be thought of, that was just in terms of kinetic energy of molecules and so on. So in the case of time, it is not self-evident that the notion of time, that there is a sort of invariant notion of time that's the same kind of thing between time as perceived by humans, time as it evolves in the universe, and so on. I think that computational irreducibility is the sort of absolute notion of time. It's the thing that is kind of the amount of computation is the analog of sort of the absolute measure of temperature in some sense. It's the thing that you can kind of compare between a brain and some physical process. You can sort of compare this amount of computation. Now, let's see, I guess so I think it's important to observers like us that we progress in a computationally irreducible way. If we could know, so one very important assumption about us is that we think we have free will. So that is important. If we're doing experimental science, it's kind of important to think you have free will, because in experimental science, if you didn't have free will, you wouldn't be able to do an arbitrary experiment. The experiment you would do would always be determined. And that means that you would be able to, but the fact that we perceive ourselves as having free will, I think, is again associated with computational irreducibility. Because if you could always know, if you could know what, you know, you're interacting with some person, the person is behaving in a computationally reducible way, you can predict what they will do. The only way that you cannot be able to predict what they will do if they are operating according to underlying deterministic rules is computational irreducibility. And so that's the thing that leads us, even though we might have underlying deterministic rules, it's the thing that leads us to believe that we have free will in the sense we're free from those underlying deterministic rules because there's